Now watch out, I could screw something up here. Integral of e to the 2t is a u substitution. It would be 1/2 e to the 2t. Okay, so that's, and then you do it again, and it's a half of e to the 2t, which is a fourth. And a half of 1/8. And a half of 1/16. And the last one, 1/32. Whew, isn't that pretty? Table full, starts plus, minus, plus, minus, plus, minus. Time to roll out the antiderivative, and I'm just going to put it right next to the original. If I follow this, it's all going to be nice. Okay, so here it goes. I'm just going to use blue to kind of keep it. My first diagonal right here is the first thing I put in there. So it's 1/2 t to the 4th e to the 2t. You pick up this sign, so you put a minus, and then you do the next diagonal. So we're going from 4 times 1/4, and so I'm going to start using the highlighter because it gets a little hard to read after that. So the next diagonal is 4 times 1/4, so pardon me as I cancel those and make it, and then t to the 3rd e to the 2t. Pick up this plus sign right afterward. You do the next diagonal. And 12 times 1/8. Do a little simplifying, so we could do 3/2 t squared e to the 2t. And then pick up that minus sign right afterward. Then 24 times 1/16, so again we're doing divided by 8, so it's 3/2 again. T, e to the 2t. Pick up that plus sign, and I think we're almost there, right? We're getting close. That was this one. And then the last one is 24 times 1/30, and the 32nd was the one we just finished with, right? So if you count them off, there's one by one, you're going down here. 1 was the first one. Then the second diagonal here with the sign, third diagonal here, fourth diagonal here, picked up the plus sign, and then we have one more diagonal, the 24 and 32, which is going to be 3/4. There's no t left, e to the 2t. Plus c, because you're done. You're out of things to integrate. That's the end of the road. That's our antiderivative. All the way down. Isn't that slick? If I made a sign error, some number error, just let me know. That method, not so bad. And it also does the ones we did earlier as well. Okay, so going down. Another example. Bring me back if you need it. So this one's, oh, we found some fun to do with this one, and it actually is a nice hint to what comes up next in the next section. There's a thing called indefinite integrals. There's something fun about this one. But the question is, hey, solve this. What does that mean? It's a differential equation. And if you remember, that simply means I want to know if you have a differential equation, solve means go find z. That's what I want. If you have the derivative and it says solve, find the regular function z. And then by giving you z equals 5 and x equals 1, we can solve for c. The plus c we can figure out. But we won't get to that until what you do is dz dx, you separate variables. So z is on the left, x is on the right. And it's kind of already separated. All I have to do is put the dx over there. So dz equals x to the 3rd ln x dx. And then you come in and integrate both sides. And that gives you z equals whatever the integral of x cubed ln x is. And of course, I'm going to use the table to make that happen. And I'll write it on the bottom row there. I'm going to put my table up high. So according to Lippitt, logs are your first choice of u. So here's my table, u, dv, and then my sign go as far as we need to. And if you get started, u is natural log of x, and then the dv is just the x cubed, right? And it goes plus first, and then minus, plus, and as long as we need to go. Okay, integral or derivative of natural log 1 over x. The derivative of that's negative 1 over x squared. It's like, then it gets kind of goofy because you think of it as negative x to the negative 2. The derivative of that would be positive 2 over x cubed. And then the derivative, that's like 2x to the negative third. The derivative of that would be negative 6 over x to the fourth. And let's see if that's enough. But you notice this is never going to end. This is going to go forever. So that will, we'll keep getting a product up here of, this will keep growing. The degree will keep growing, and the denominator will just never end. Integrating x to the third gives us 1/4 x to the fourth. Integrate it again, you add 1 to the power and divide by it, so that's 1/20, because 4 times 5 is 20, x to the fifth, and then you integrate again, so it's 6 over 20, oh my god. So, when do you stop? That's the million-dollar question. Both these go forever. So, here's what you can do. You can just write out a big long one, and just keep going. So, I'm off to the side here. Imagine I'm going to just write for a little while and just show you this is a possibility. I could just do each diagonal, so 1/4 ln x, or x to the fourth, so it could be this. Put on the minus sign, and then you do the next diagonal. Now 1 over x times x to the fifth, at least that cancels a little bit, so it's 1 over 20 x to the fourth plus, and then I do my next one, negative, looks like it's going to be x to the fourth again. Negative 1 over 120. X to the fourth, put on the minus sign. And then, I don't know, you just keep on it rolling, dot, 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 and that's going to keep rolling. So you have to figure out when to stop. All right, I'll tell you when to stop. Pick a spot where you can integrate. This is the process of, if I stop after one rotation, here's u, this is v, and the way integration by parts is, it's u times v, so those yellow, two things that I highlighted in yellow, that'd be u times v minus the integral of v du, and if you remember, this is du right here, and remember the one to the right, this is v right here. So for tabular method, if you do one diagonal product, tack on the sign, the minus sign afterward, and then just integrate the row where you stopped, that's actually one iteration of what's regular old integration by parts. So I'm going to write what I have here. That'd be 1/4 x to the fourth ln x. So that's my first diagonal. You just do one diagonal. Tack on the minus sign, and then wherever you stop in that table, you just integrate that last row, because it's actually technically, that's u times v minus the integral of v du. Okay, so I put 1 over x times 1/4 x to the fourth. If you're okay with, I'm just going to put 1/4 and then 1 over x and x to the fourth make x cubed. Okay. You can stop like that anywhere in the table. We could have gone a couple of iterations down and then took an integral and stopped. You can choose how you want to stop this thing. You look at each of those rows and you stop when it's repeated like this at the first sign of an integral you can actually integrate. So you don't go forever. You're more than welcome to if that makes you happy. But if you can just, each row, when you see that repeated pattern show up, just go, can I integrate this row if I put those together? Yeah, I can do that. That's just 1/4 x cubed. That's when you stop, as soon as you can integrate. So instead of the never-ending story, so we stop right there. 1/4 x cubed is integrable. You go with it. That'll happen. You'll get this never-ending u and dv column. Don't go forever. Just look for the first row where you can integrate. That's one sign. With polynomials, it just stopped on its own. With this situation, you look for when you can integrate. There's one other scenario we run into where we'll just deal with that when we get there. It's a little bit later. But now we're good. Just play with it. I think we can just integrate that one. I'm going to write z is 1/4 x to the 4th ln x. And then minus 1/4 x to the 4th divided by 4, so it's going to be minus 1/16 x to the 4th plus c. And that's the general solution. We like general solutions, but this one gives us a c possibility by putting in 5 and 1. So you get 5 equals 1/4 ln of, okay, 1/4 times 1 to the 4th. ln of 1 is 0. So that first chunk, if I put 1 in for x, is 1 to the 4th times ln of 1, that's 0. The second chunk, you put in 1 and you just get minus 1/16 plus c. And so our c is going to be 5 and 1/16, 81/16. That's the end of our story. So the general here, but the specific solution with our given c is all of this plus 81/16. Stop at the first row you can integrate if it's repeating like that. Yay, that's a healthy start. So the only thing we should do now is go back to the ones we've already done and show that the tabular method would be really awesome back then. And then you should just practice. Should we do that? That's a resounding yes for those of you who can't hear it on the microphone. Okay, just being silly. There it is. Look at number 2. Once upon a time. You got to pick your u. Who gets u priority? Exponential or polynomial? Polynomial wins just by 1 letter, so that's it. So you go, u is your poly, oh poo, dv, and you go, start with a plus. My u is 2x, e to the 4x, got it. And then we take derivatives on polynomials so they can't, 2, 0, 1/4 e to the 4x, and then you integrate one more time. Oh man, we gotta go one more time. So what is that, 1/16 e to the 4x, plus minus plus. So the integration of this, first diagonal, right here, I'll do highlighter, pick up the negative, so that's 1/2 x e to the 4x. And then minus the next diagonal, 2/16, 1/8 e to the 4x. And we're done from there, plus c. Once you get to the end of the row. And if you look back at what we did last time, same result. But man, that went a lot faster. Gotta love that. Uno más. Let's do x ln x. Who wins in that battle? Log or polynomial? Log. Good call. Here goes. So let's do another log. We know log's trouble. Nothing but trouble. Ln of x. We got x. Start with a plus. And we all know it's going to be 1 over x. And it's going to be negative 1 over x squared. Oh my word. And then it's going to be negative 2 over x cubed. It just keeps going, and it's 1/2 x squared. And then it's 1/6 x cubed, or something like that. Just never ends. So when do you stop? As soon as you can integrate. So that first diagonal looks pretty good. So I'll put it on there, make some room up here. So uv, that'd be 1/2 x squared ln x. Bless you. Minus, you pick up the minus sign. Can we integrate if I stopped at the second row? Is that integrable? And that totally is. That simplifies to 1/2 x. So let's do that. So that's the integral of 1/2 x. Because the 1 over x and x squared cancel. So at that point, Just need to finish off the last part. 1/2 x